Unit 4 is all about exponential and logarithmic functions, and today we're going to focus just on the exponential stuff. Now, to kind of get us ready to rock on that, let's take a look at the warm-up. The warm-up we're asked to evaluate the following. The following being 2 to the third, 2 to the fifth, 2 to the 1/2, and 2 to the negative 2. Starting off with 2 to the third, it's 2 times 2 times 2, which gives us a grand total of 8. 2 to the fifth is 2 times 2 times 2 times 2 times 2, which is 32. Now, exponents of that are fractions. You end up doing the root, in this case, 2 to the 1/2 is going to be the square root of 2. Now, side example here, if you were to have, say, something like 8 to the 2 over 3, what you would do is you do the third root of 8 squared. So the denominator is what root you're taking, the numerator is what you're going to raise that exponent to, or sorry, what exponent you're going to raise it to. 2 to the negative 2, remember, that's the same as taking 1 over 2 to the positive 2. Essentially, take the reciprocal and apply the positive exponent. So we end up with 1/4. So our goals for this lesson are to write and evaluate exponential expressions to model growth and decay situations. So there's a video there. I'll post this on below as well in the Canvas link, so you can check that out. But watch this video, and I'm going to ask you to fill this table, but I'm just going to kind of give you the summary of it. The video is kind of doom and gloom. It's talking about population, and it's growing and growing and growing and growing and growing, talking about bacteria. Don't worry too much about the details that are doom and gloom on here. But essentially it says, starts off with one bacteria at the beginning, and then bacteria just kind of like exponentially grows. It's going to have 2, and then after 2 minutes, it's going to have 4 bacteria. Then 3 minutes, it's going to have 8, and 4 minutes, 16. 5 minutes, 32, 6 minutes, 64, 20 minutes, wait, this pattern doesn't continue then. We got to maybe figure out what we're going to use to help us come up with the next value. So we're going to come up with a model, y equals, and it looks like, looking at our pattern, this is like 2, this is 2 to the second, 2 to the third, 2 to the fourth, 2 to the first, 2 to the 0 over here, and then we got 2 to the fifth, 2 to the sixth, and this one we're going to have to do 2 to the 20th. Now, folks, you can type that into your calculator. It's going to be, oh goodness, I don't have this in front of me right now. It's going to be, and I can't even fit it in there, 1,048,576 bacteria after 20 minutes. Let me move my picture a little bit so you can actually see that number that I just wrote. But it's going to be 1,048,576 total bacteria. So the equation we're using is y equals 2 to the x power. You could also do the 30th. It's going to be much, much, much larger than what we had. If you want to apply it to be a little more specific, you could say b, your number of bacteria, equals 2 to the t, 2 to the power of time. Now, we're talking about growth here. In this case, growth that is growing, doubling every minute, can be modeled by a function using a variable as an exponent. In other words, it's no longer like x to the second. It might now be, in this case, 2 to the x. We call this an exponential function. So an exponential function, f of x, he has a base, and we're going to call that base b, and the exponent, in this case, is our variable. And we're going to say b is greater than 0, so we're not going to deal with negative values there for now. And we're also going to say b is not equal to 1, because if you raise 1 to an exponent, well, 1 to any exponent is always 1, so it's not super interesting there. Let's take a look at an example here. I would encourage you to use Desmos or a graphing calculator or whatever to graph the function y equals 2 to the x. Let me shift this down here again. So if we graph y equals 2 to the x, this is what our table would look like. The graph, if you were to visualize it, would look a little something like this. So here's 1, and it's going to look something kind of like this. This is not a 2-scale representation, but it's good enough to be honest. So our domain on this one would be x is any real number we want. The range, looking at this graph, now my graph is not a perfect representation of it, but the range, we're talking about the y values, those are also real numbers. But looking at this, the graph's not going to, and this is going to get into the special thing, it's not going to cross the x-axis. So we're going to say y greater than or equal to, or sorry, just greater than 0. So we're going to have y greater than 0, and again, the special thing is it never touches y equals 0. It's going to get really, really close on the left side. If you use your graphing calculator and scroll really, really far, eventually your graphing calculator will say it is equal to 0, but that's just because it's rounding. It might be 0.00000000003, and it'll just round to 0. So it's not quite exactly 0. Now, similarly, if we had 0.5 to the x, this one would look a little something like this. It's pretty much the same shape where it would go through, but in this case, it's going down and to the right. The domain on this one would still be the same. You can still plug in x as an element of the reals. You can plug in any x value that you'd like, but the right side is now the one that's going down. Sorry, I started thinking of something else. So our range is y as an element of the reals as long as our y values are also greater than 0. That part's still the same. So the special thing again is it never touches y equals 0. Now that special thing has a name for it. We call that name an asymptote. An asymptote is a line the graph approaches. Now we could be a little more specific because in many cases for what we're going to do, it's never going to touch that line, but unfortunately that's not always the case, but for what we're doing, it's effectively that. So it's a line that the graph, I just wrote the graph twice, approaches. And it could be like the x-axis, like we were approaching on the last two examples, or it could be a vertical asymptote, which we'll talk more about later. Folks, we're going to talk about specifying between growth and decay. So what I'd like you to do is take a look at those images, graph those in your graphing calculator, and tell whether it shows growth or decay. This first one, the general graph would look something like that. That represents growth. The next one, if we have 50 times 1.32 to the x, that would also look like that. And that would also be growth. For that last one, 22 to the 0.9, or times 0.9 to the x, would look a little something like this. And that would be a decay. Oop, misspelled that. In general, if the absolute value of your base, and we're really just focusing on positives right now, but I'm going to keep it as the absolute value of our base is greater than 1, we have growth. So whatever's being raised to the exponent, if it's greater than 1, we got growth. Now if it's a small number like 0.98, so we have 0 less than our absolute value b less than 1, that's a decay. So a couple more things relating to this. This is an exponential growth and decay percent formula. So you can model the growth and decay by a constant percent increase or decrease using the following thing. A of t is your final amount. A is your initial amount. We're going to use a different letter for certain situations. And then it's going to be 1 plus r or minus r. It's going to be plus if it's a rate of increase and minus if it's a rate of decrease. But and then with all that's being, or that parenthetical groups can be being raised to the t, your number of time periods. So let's take a look at an example here. A man has an initial amount of $2,000 in a bank. He earns 2% interest every month. Write a formula expressing the amount of money he has in the bank after t years. So I'm going to use the formula A of t equals A times 1. In this case, we're growing in interest. So I'm going to say 1 plus r to the t. Now, what we know is $2,000. $2,000, that's our initial amount, the amount we're going to be plugging in. 2%, so I'm going to write this down here, A equals 2,000. Our rate is 2%. Now, when we are writing this in an equation, we got to convert it to a decimal. So remember, we're going to divide it by 100. In other words, we got to move it 2 decimal places to the left. So we're going to have 0.02. And then t is just our number of years. We're going to leave it as is. It's going to be if t is our number of years, it's going to be years times 12 if we're doing it every month. So plugging this in, we got A of t, equals A value of 2,000. We're starting off with $2,000 times 1 plus 0.02 times 12t. So we're doing it 12 times a year. Let me move my image so I'm not covering it up. You can clean this up just a little bit more by adding the 1 plus 0.2t, or 1 plus 0.2. So we have 2,000 times 1 plus 0.02 is 1.02 raised to the 12t. Now we can also, on the next example, we're going to come up with an equation for it, and then we're going to actually solve for a value. So in 1981, the Australian humpback whale population was 350, and it's increased at a rate of 14% each year since then. Write a function that models the population growth and then estimate the population after or in the year 1995. So our initial amount, our lowercase a value is 350. Our rate is 14%, which is 0.14 as a decimal. Now, plugging that into the equation, a of t equals 350 times 1 plus 0.14. Since we're increasing, we're going to add the 0.14 raised to t. In this case, t is just years, so we're only going to have to do t, not 12 times t, because it was months in the previous one. Now, that is the generic equation. You can simplify it a little bit, which we will in a second. But now we're going to ask to plug in the years for 1995. So 1995 would mean t equals 14. 14 years after 1981. So we're going to do a of 14 equals 350 times, I'm going to consolidate the 1 plus 0.14 to 1.14, and we're going to raise it to the 14th power to figure out how many whales there are. Now, I'll be honest, I didn't do this ahead of time, so I'm doing it right now. So I'm going to type this into my calculator, 350 times 1.14 raised to the 14th power. So you can see, if you want to zoom in, the lights are off, so it's kind of hard to see. But I'm typing that in exactly as I wrote it. I'm going to hit enter, and we end up with a of 14 equals, and then the decimal, we got 2191.47, etc. But folks, sometimes we have to think about context. We're talking about whales here. We're not going to give 0.47 on a whale. So we're going to say it's approximately equal to 2,191 whales.